insert the identity operator in between here. I get this equation to solve. Some genius came up with this idea that this equation is a lot better than this equation. Okay. The two guys who came up with this equation is actually Xiao and Klein. He came up with this equation to solve. And then if you want to take advantage of this equation with your prior knowledge, you spend half your career in solving this problem. So you know how to construct these matrices very well. And then you can construct the matrix system for this by just doing a simple trick like that. Yes?
In this equation, when that inner product, no, the delta U, when the FAE inner product with LFE equal to 0, the first order difference no longer can be 0, right?
You mean this becomes 0?
Yeah.
This can never become 0, right? Why should it be 0?
What if the exact solution makes this to be 0?
This will give you G exact, G, right?
Mm-hmm.
This inner product is, let's assume that it's never 0.
Okay.
Why should it be 0?
So
most of the time it's not 0. Then if it's 0, it must be accidental.
Yeah. So is this a restriction for this Jones code?
Yeah, we hope that it doesn't become 0. If it's 0, then we are in deep trouble. Because we also have this in the denominator, right?
Yeah.
So we'll be in deep trouble with the Jones quotient if we have this been 0. Jones quotient will not be valid anymore. Okay?
You also mentioned that you can use Jones quotient to improve accuracy, right?
Right.
How do you do it?
Well, you try to calculate the desired value that you have using that function now, instead of calculating the quantity that you have directly. What I'm saying is that, say if you have a measurement that is HF, you calculate this measurement directly, right? But instead you can use this Jones quotient to calculate this thing. You use this Jones quotient. If you make the first order error in your solution, you get the second order error in U. That is the idea. It's very similar idea to Rayleigh's quotient in quantum mechanics when you want to find the eigenvalue of the system. Okay.
So all you're saying is if I want greater accuracy, I use the second formula instead of the first.
Right. I should get better accuracy for U compared to just using this formula. There's something called the Rayleigh quotient too, which is very similar. You can prove that LF is equal to lambda F, and you can define the Rayleigh quotient, which is something like FLF is equal to F for the eigenvalues of the system. If you make a first order error in F, you can prove that the error in the eigenvalue is second order. Okay, physicists use this a lot to find energy levels inside the atoms because those are eigenvalue problems. So what I'm supposed to prove to you is that if I have an expression something like this, how can I exploit this variational property and come up with this Rayleigh-Ritz procedure to convert this into the matrix system, and how the Rayleigh-Ritz procedure can give me insight on how to pick my testing function or my weighting function. These are called testing or the weighting function. Okay, properly, and how can I choose my S of n properly? Okay, and this is just a motivation. Hui, you get this right? Why we need to do testing? If we don't do testing, then we still end up with an infinite dimensional system. If I don't do testing at this point, the system is still not manageable. I have to convert it to a square matrix system, which is manageable. Okay. So let's go ahead with the Rayleigh-Ritz procedure then. So the idea is actually quite straightforward. You let f be expanded in terms of a set of basis functions. These are called the basis functions, or sometimes called the expansion functions. Okay? And then you have two problems to solve. In this problem, one is LF equals to G. The other one is L transpose F is equal to G auxiliary. So I have the original problem to solve, as well as the auxiliary problem to solve if L is not symmetric. So it's slightly trickier. So I also have to define a set of basis functions for the auxiliary problem. Let me call those FAN. N is equal to 1 to N. Okay. And now if I substitute that in there, then the inner product FA LF can be approximated by this substitution. And if I do that substitution correctly, let me use n prime for one case. Okay? If I do the substitution correctly, I will have m prime as one summation and the other summation as n, and then I will have bn prime, fan prime, L, f n an. Okay, can you see that? Can you see that substitution? Aditya, can you see that going from the left to the right hand side? I substitute this and this into this expression because that. Okay? So this is just a matrix element Ln prime n, right? Ln prime n. And the right hand side is actually the inner product between. So I have converted an infinite dimensional inner product into a finite dimensional inner product. Of course, this is an approximation because I have projected the inner product into a finite dimensional subspace by this substitution. So I can do the same thing to this thing over here. Okay, FA G, if I do this substitution, will just become, if I do this substitution, okay, Bn, comma, FA N G would be just equal to N Bn Gn. Okay, so this inner product becomes just equal to B transpose dot G. Okay, and then the third term will just become GA. F will just become G. I'm calling this thing Gn. Okay, I'm calling this thing Gn. This will just become GA transpose dot A. Okay? So can you see how the procedure goes now? So I have projected an infinite dimensional functional defined in an infinite dimensional space into a functional defined in a finite dimensional space. So instead of working with this exact variation expression, I can work with this approximate one. Would be just equal to, the first term becomes just this one. The second term just becomes that thing over there. And then the third term just becomes GA transpose dot A. Right? That is the first step of the Rayleigh-Ritz procedure, which is to project this thing into the subspace. And then this again is kind of quadratic because it has a product of the two unknowns. A and B are unknowns to be solved. Okay, so this is still a quadratic function now in a sense. And we can easily prove that this is also variational. The minimum point is also something that minimizes this quadratic function now. Okay? So what we need to show is that there will be an optimal A and an optimal B that minimize or optimize I tilde. Okay? There will be something that optimal because it's quadratic. And then if you perturb the solution A about the optimal solution, calling it departing by delta A from the optimal solution, B is B optimal plus delta B, then we can show that the optimal solution is a solution to a set of matrix equations. How do we do that? We take the first variation of the above, we get delta B transpose dot L dot A optimal, okay, because we are perturbing about the optimal point, plus B optimal transpose dot L dot delta A, and then we perturb B about its optimal solution, and then minus G transpose A delta A. So this is the first variation. And in order for this to be an optimal solution, it must minimize this. So this must be 0. Okay, what I mean is that I have this I tilde, and then it will be a function of A and B. And then about the optimal point, this function now must be minimum. In order for that function now to be minimum, this first variation must be 0. That is the definition of AO and BO. Okay, they're defined to minimize this. So if this is to be 0, then you can see that these two terms must cancel each other. They cancel each other. And that these two terms must cancel each other. Okay? So if that is the case, then we get the fact that LA naught, if they cancel each other, must be equal to G, and then L transpose dot B naught. If these two terms cancel each other, must be GA. Okay, this equation is actually B naught transpose dot L is to the GA transpose. When you take the transpose of this, you get this equation. So those are the two equations that we need to solve in order to obtain the optimal solution that minimizes this functional. Okay, this functional is the subspace approximation of the original functional. So this gives us some insight. That means that we have to choose our basis functions and the testing functions in such a way that they form very good solution or form a very good approximation of this subspace functional. And then how do we choose those testing functions? We choose our testing functions to solve the auxiliary problem accurately. We choose the testing function so that, you see, this is the testing function or weighting function. So when we form this matrix equation, okay, L is actually FAN prime LFN. So the testing function actually comes from the auxiliary problem. So if the testing function solves the auxiliary problem well, it will minimize this functional, and also it will minimize this approximate functional and give you a good solution. So the insight is that the testing functions will be chosen so as to solve the auxiliary problem. Wow. So what does it mean? What does that mean? Well, this is called the right domain space of L. This is in the right domain space of L. But what is FA? FA is in the left domain space of L, right? Because it is in the domain space of L transpose. So it should be in the domain space of, it should be in the left domain space of L. Can you see that? Okay. This is in the right domain space of L. This is in the right domain space of L transpose. So this FA is in the left domain space of L. Okay. The matrix operator A has two domain spaces. It operates on vectors on its right, but it can also operate on vector in the other direction, and in that case you can write it in this manner. So this is in the left domain space of A. This is in the right domain space of A. So the testing function should be chosen so that they solve this auxiliary problem well. What does it mean? What it means is that it should be chosen to approximate the left domain space of L. If L is not symmetric, its right domain space and its left domain space are different. Okay? So you should choose the testing function that approximate the left domain space well. You should choose the expansion function to expand the right domain space well. That's what this exercise tells you. What is the left domain space of an operator L? The left domain space of an operator L, say, if I write it in this manner, by the definition of the transpose operator, I can always write this in this manner, right? This is the definition of the transpose operator. So what it means is that W is in the right domain space of L transpose, which is correct. But if you look at this expression, W is in the dwarf space of LF, because we say that any vectors that you can form an inner product with another vector, this vector is in the dwarf space of this. Okay, so you can see that with that identity, you can see that W is in the dwarf space of LF. Okay, LF forms a vector. This vector has a dwarf space, and W is in that dwarf space of LF. Another thing you can see is that W is in the domain space L transpose, right? That's what it says. So actually, this proves a point, which is that the domain space of L transpose, or the left domain space of L, is the same as the door space of this function, LF. Okay. So when we choose the testing function, we should always choose this testing function to be in the door space of LF. And you see this being quoted a lot in the literature. People always say, choose your testing function to be in the door space of LF. So as I said before, in electromagnetics, you always have inner product like this. So the door space of J is E, the door space of E is J. This inner product are called reaction inner product. J has to be divergence conforming. We said that before, because divergence of J gives you charge. Okay? E has to be curve conforming. So this live in a Sobolev space where there are some restriction on their derivatives as well. So if you have a linear vector space where you define certain smoothness about this function, those are called Sobolev spaces. So you can see that whenever you have a divergence conforming function, it has to be tested with a curve conforming function. Whenever you have a curve conforming function, it has to be tested with a divergence conforming function and so on, in order for this inner product to make sense. So you can take a look at, say, in electromagnetics, you might want to solve this equation. So this is an equation something of this form. Okay, something of this form, where this is your unknown. If you look at this L operator, so this gives you H. This gives you E back, right? So if you have an E over there, E is curve conforming. How should you test this equation? You should test this equation with the divergence conforming basis function. Okay, you should test this equation with divergence conforming basis function. So I think that turns out to be the case if you expand this in terms of a, let me see, does this make sense? Now let me think a little bit more about explaining this in this context. But I know that for EFIE, like if you have an equation something like this, and this might be your integral equation that you have in electromagnetics. Then you have to think about how to test this equation well. This actually gives you E field. This gives you E field. So this is curve conforming, and you have to test it with this door space, which means that you have to test it with divergence conforming basis. So you have to form a variational expression, something like this. This is divergence conforming, and then if you form this equation, then and you may choose a set of testing functions to be divergence conforming to project this into a smaller subspace. Okay, that I know for integral equation to be sure, and that is the way you should test this equation. I think if I think a little bit about it, that rule also is applied in the FEM method. Okay. So that gives you the motivation on how to pick your testing function. Testing function should be a good approximation to the auxiliary problem, and they should be in the door space of the equation that is defined. Okay? So are there any questions? Okay? I hope that this gives you a higher level understanding of all the numerical methods that you're doing. Oftentimes you just bury your face to the numerical method and do all the integration in all the tiny little details, but you don't worry about the big picture. What is the big picture? Above all this coding that you do, you go to the computer and punch in a lot of codes, right? And then do a lot of integration and form your matrix element with FEM or method of moments, but you never ask what the bigger picture is about those busy work that you do. And hopefully this gives you the bigger picture of what actually is happening above all the busy work that you're doing. Okay? Is that good enough? So you can read the rest of chapter 5. Okay, I can talk about eigenvalue problems, but I guess I will not talk about it. I talk about that quite a bit in the waveguide theory course, because when you need to find modes of resonant cavities and you need to find waveguide modes, you cast those into eigenvalue problems. Okay. I'd like to move on to talk a little bit about chapter 6, which is on mode matching. Mode matching is what I actually discussed in chapter 6. And there's this physics of mode conversion that you should know. I talked quite a bit about this in the waveguide theory course, so I won't dwell on this too much. But this is good for solving problems that are highly complex due to the curse of dimensionality. Say if you have a 3D problem to solve, essentially it's very time consuming because your unknown counts are very large. So one way of overcoming the large unknown counts that is done a lot in optics and microwave engineering is to try to reduce a 3D problem into a set of 2D problems, or 2D problem into a set of 1D problems. Say if I have this 3D inhomogeneity. I can reduce this to a set of 2D problems by solving a 2D problem in this section, a 2D problem in this section, find all the modes that I have there, find the 2D problems there, and then match the solutions after I found all the possible modes. Okay. So if I put a source in one region, say, if I excite all possible modes there, those possible modes will propagate downward and upward away from the source, but when it hits the boundary, it's not like a simple homogeneous medium boundary that you have learned in chapter 2. There will be the physics of mode conversion, in the sense that if you just have one mode coming in, if you just excite one single mode, if you're clever enough to design a source to excite one single mode, the mode that comes in will bounce back with many, many modes. All the modes will be excited because of the asymmetry introduced by this discontinuity. And then if you just have one mode coming in, it will spear forward a whole bunch of transmitted modes. Okay? It will spawn a whole set of transmitted modes. And then there will be infinitely many modes that are transmitted, infinitely many modes that are reflected, and then you have to find the solutions by mode matching across this interface. You can use that to solve laser problems. This becomes a very popular technique in laser technology, for instance. Using mode matching, you can use that to solve geophysics problem, because the Earth is quite inhomogeneous. You can use this to reduce a 3D problem into 2D problem. Laser technology. optics. Okay. So there are many problems that can be cast in this form. But let's talk about a very simple case. Let's talk about a very simple case so that you can understand, okay, before we talk about very complicated case. So if we have two parallel plates, you can easily count the modes we have inside. You might have a fundamental mode, and then you might have a second mode, you can have a third mode, you can have high order modes and so on. So you can count the modes and solve for them very easily. And say if this is K0, then you find that the number of modes become, if I call this Kx, for instance. I think I use Kx in my book. Okay, I don't recall now. Okay, because I usually like to use this to give a z direction. So if you look at a complex Kx plane, the modes will usually have Kx less than K0. There has to be a mode because these modes are bouncing wave modes. You can think of this mode as coming about because the wave bounces around. Because if they're coming about because the waves are bouncing around, Kx must be less than K0. You can only have Kx equal to K0 if you have a TEM mode. So if you look at the distribution of these modes, if K0 is here, those modes are distributed. Like this, for a parallel plate waveguide, you have a TM mode, you might have also the TEM mode that actually is distributed over there. Okay? This corresponds to the picture we have in chapter 2. And after a while, you will see that the modes will be cut off and they become evanescent. So this is imaginary Kx. This is real Kx. The mode distribution will look something like this. These are evanescent modes. These are propagating modes. Okay? So this looks like the branch cut we have in chapter 2. And you can also find that if Kx is a solution, the other solution propagating in the other direction is also a solution. So you also get a whole bunch of modes that look like that. With a mirror symmetry of those modes that you found. Okay, so if they're evanescent in one direction, it can also be evanescent in the other direction. So these are the modes that you have inside this parallel plate waveguide. How do we connect this to what we have learned in chapter 2? What happens if you make the spacing h larger and larger? What happens to this distribution of modes? If we pull the parallel plate apart, what happens to them? Do they become denser, sparser, or they disappear in thin air? What? They should become sparser and sparser. Okay, Aditya's suggestion is that if I pull the parallel plate apart, the modes become sparser and sparser. Suggestion 2. Anybody? Yes? Denser and denser, right? Remember this thing? Kxn is n pi over h. It's a mode number. So if h becomes bigger and bigger, delta Kxn, the difference between adjacent mode is pi over h. So the modes will become denser and denser. So if you put the parallel plate apart, you have more and more modes, okay? And then it becomes densely populated on the real and imaginary axis. And in the limit when h goes to infinity, you have the branch cuts back. Those modes are just lining themselves with the branch cut. So you get back to your knowledge of chapter 2. So if you have a bounded region, there's no branch cut, right? You also learned from chapter 2 that the branch cuts are associated with the first and the last region. Nothing. No branch cut is associated with the intermediate region. So if you have this problem, there's no branch cut in this problem. But then if you make the space infinitely large, then the branch cuts come back. Okay? So this is the picture you should have of the mode of that system. But what happens if you have a mode of a system that's slightly more complicated? I have a dielectric slab. Enclosed between two parallel plates. And I start looking for the mode of this structure. Very similar to what I did over here. Do you think that those modes will be discrete or continuum? You probably solved this problem in your undergraduate course for a dielectric slab problem, right? And if you were to look for those modes, would they be discrete or would they be a continuum of modes? Okay, actually it turns out to be discrete. You find that the modes are discretely distributed. There could be some modes that are trapped inside the dielectric slab. This is K1, K0, K0. If K1 is larger than K0, there could be some modes trapped inside the dielectric slab. So the distribution of the mode will look something like this. This is K0, this is K1. So there could be some modes that are bouncing back and forth inside the dielectric slab. But they can never be larger than K1 because they're bouncing waves. So the modes will be something like that. And these are the trapped modes inside the dielectric slab. But then there will be some modes that are outside, propagating like this, bouncing around in the outside region. Those modes will be like this.